So hi guys, so in this video we would be processing with the previous notebook that we have been working on, that is generating music with RNN. So as I told you in the last video, in this video we would start from where we left. We would be starting with creating our own Midi file, and we can generate our own Midi file from a list of notes using the function below. So what we are doing here for this particular thing, notes to mid, we are taking the notes, the output file that we will be defining the instrument and the velocity to for the note loudness, and then we are just taking the pretty Midi instrument name to program file and library, and we are directly converting it. And this is the function which we have defined for I note in ith rows, and we are defining three parts: start, end, and note, and we are directly appending it into the instrument notes. So I've just done this, and after that we can just do this thing in the example file, that example.midi, and let's play the generated MIDI and see if there is a difference. So yeah, this is the display audio which we would be getting. So if you want, you can play this in your device and just see if you can feel that difference, and if you want, you can even download this from here. I won't be downloading it because I have downloaded it twice. So now the next step we would be doing is creating the training data set, because this was just one example we were doing, and even in this example we haven't created anything new. We just made a MIDI file for exactly converting a whole note, for making our whole music. We would need to create a training data set for training a model. So we would be doing that by extracting notes from the MIDI files. So we can start with a small number of files and experiment with the more. This will take a couple of minutes. So we are taking 5 files, and for f in them we are taking all notes.append, and we would be doing this. I would be just doing this, and it's processing it. It would take a bit of time, I know. And now the notes, the length of the notes, this is the notes passed, it's 20,663. We took just 5 files. Now we would create a tf.dataset from the past notes, and the orders we would be doing is pitch, step, and duration. So for training notes, what we are doing, we are creating a stack, np.stack, and for all notes in the key, for key in key order, means we are going in the chronological order. So I'm just doing this, and yeah, so this is the part, the notes, we are converting it tf.data set from tensor slices. So if you don't know about this, you can directly go and google this. I have actually already explained this in some of my previous videos. So this is how you can see the creates a data set whose elements are slices of the given tensor. Nothing very different. This is all already available in the existing data structure part that we have already studied in previous models. Now, you will train the model on batches of sequence of nodes. See each example, which consists of a sequence of nodes as the input features and the next node as the label. So this is the we are creating the sequence, the data set, the sequence length, and the vocabulary size length. So so what would this do? tf.dataset, it would return a tf dataset of sequence and label example. So we are taking one extra for labels. We are flattening the dataset of datasets into tensor in this, and then normalizing the pitch node. We have did this in even the previous video, and then split the labels. So I would just run this, and the function has been defined. Congratulations. Now set the sequence length for each example. So the sequence length would be 25. Actually, you can try it with a lot of different things, different lengths like 50, 100, 150 to see which of it use. The size of the vocabulary is set to 128 to represent all the pitches supported by Pretty Mid. So this is which we have already taken, something that is already present on Google, and the sequence length is 25. If you want, you can take 50 also. Like if I wanted, I could have taken 50 also here. That won't have been a big issue. If you want, I can run this for you, and yeah. Now the shape of the dataset is 101. I mean, the model will take 100 nodes as input, but for now what I would do, I would just put it as 25, because then I would have to change a lot of things down here, and I don't want the results to change once again. So I would just run this, and yeah, so this is what we get, the sequence shape and the sequence elements of the first 10 tensor. So the shape of data sets clearly is 100,1, meaning the model will take 100 nodes as input and learn to predict following node as output. So out of 100 nodes, it has learned this thing. So it's pretty good. Now the best the batch the examples and configure the dataset for performance. So we would the batch 64 and buffer size equals to the number of items in the dataset. That is directly nodes length and the sequence length. And what we are doing for training data structure, we are giving it sequence data structure, and we will shuffle it with the batch buffer size, and batch size we have given here, and the cache and the prefetch. So we would just run this with auto-tune, and let's take a look at what is happening here. So if you see here, you would observe that tensor spec, shape, d type, everything has been mentioned, the duration, type, and pitch step. These three things we have defined from the very beginning that we would be using for creating and training the model. Now the model will have three outputs, one for each variable, because we are giving it three variables now. We just talked here duration, pitch, and step. So for step and duration, you will use a custom loss function based on mean squared error. If you have seen my previous video in which I have talked about custom loss functions, you must have got an idea what I am talking about here. So this is mean square function with positive error. You are giving it 2 input, it is taking that, and yeah, it's super easy. I would just run this and tf.reduce mean, and it is taking that positive pressure. This is something new, but yeah, it is also done in a lot of examples. So now the input shape is this, sequence length comma 0, the learning rate is 0.005. The input layer is tf.kera's input LSTM, and LSTM we have used a lot in natural learning processing, if you remember. And the pitch, we are using dense layer, step dense, and another. So 3 dense layers for specifically for them. And the model is tf.kera's input. The loss function is this, and yeah. So the optimizer we are using is Adam, and the loss function we have already defined above. So for the loss functions we are using 3 specific one. For step and duration we are using custom loss function, that is mean squared error with positive pressure, and for pitch we are using sparse categorical cross entropy. So I would just run this. Yeah, we are done. This is the whole model, the first input layer, then LSTM layer, then the dense layer, and the 3 dense layer specifically for duration, pitch and step. So now the testing the model. So test the model using the model.evaluate function. So you can see the pitch loss is significantly greater than the step and duration loss. So I would just do it, and yeah, it's happening here. Yeah, so the loss is 5.1 for the loss is this, for duration loss is this, the pitch loss is 4.85, and step loss is 0.14. so the pitch loss is, I think, a bit greater than when you compare it to step loss, and yeah, it's totally fine. I guess that is not something to worry about, because the loss is the total loss computed by all three, and the significant part contributed to is by pitch loss. And the only way to balance it, the pitch loss, is to use the loss widths arguments to compile. So while we are compiling this, we would use the loss widths thing. For step and duration we would put it as 1 only, but for pitch we will use 0.05 to make sure it's a bit low here. We don't want a lot of loss to happen. So yeah, and I would just run this cell and this cell to now return what is happening. And yeah, things haven't improved that much, but I would say it's better this time, because the total loss is 0.5 now. So then the loss becomes a weight sum of the individual losses, because it is getting multiplied by 0.05 definitely. So yeah, it's going better that. Coming to the callbacks, we are using verbose as 1, patience as 5, the file path we have already defined here, early stopping, and the restore best weights equals to true. So yeah, so I won't be running this particular cell because it would take a lot of time. You can run it, but I won't be running it because it would take around 8 to 9 minutes to compile all the things. Now coming to the part, I would just directly show you the examples, and yeah, this is how it looks like. And I guess I would have to turn off the dark mode for showing you all this clearly. I would just do this again, and yeah, so you can see this is the loss, and it looks good. It is at last decreasing, and now we would be generating the nodes, now the most significant part of the notebook. So to use the models to generate nodes, we will need to first provide a starting sequence of nodes. the function below generate one node from sequence 2 nodes. So yeah, now coming to for pitch node, it draws a sample for the softmax distribution of nodes produced by the model. So this is predict next node, and these are the three things we are giving it: nodes, Keras model, and temperature. So now what we are doing, we are adding a batch dimension. Now these are the predictions, model.predict, and the step, the duration, the pitch logits, and we are defining everything here in this function to make sure that we get the generated nodes. For that we are using three things: definitely the nodes we have taken, the already trained model, and the temperature part. So the temperature part is basically being used to normalize things, to just make sure that everything works okay. And yeah, it has been done. So now we will generate some node. You can play around with the temperature and start sequence in next node and see what happens. So I would just run this, and it is being trained. It takes a bit of time, but yeah, now we will see the head part to see how it works. So this is what it generated, and yeah, it looks good, I guess. It has been step, duration, start, and it has generated some random things, I guess. Now coming to output file, we would just display that audio, and if you want you can even play this audio. I won't be downloading it because as I told you, I've already did it twice. And let's see at the generated node. So this is how it looks like, the whole track, and it looks so awesome that it works really nice in that. So yeah, this is the coming to pitch, step, and duration. It has worked really well. Now let's play with it a bit differently. Let's set the temperature to be 4.5, I guess, for that asset, and it has been already defined here. So yeah, it is being trained, and once that happens, I would just generate the nodes, and you will see a difference this time. Believe me, you will see a difference. So you can see, I guess, a bit more difference than we were expecting. And yeah, let's see what it has got output for us. Oh, I just by mistakes. So let's see what it has given us. Okay, so this look a bit different and complicated than what we just generated a minute back, but yeah, it's definitely a music tone. So yeah, it's all depending on how you set the variables accordingly, especially the temperature one. I would just put up some note for temperature for all of you, so that you don't get confused that what is this temperature variable exactly doing here while playing with this notebook. Yeah, so that is it for this video. I hope you have enjoyed this notebook. This was one of my favorite notebook I have means played with, and I would just give the link to this notebook as usual in the description section. You can go and play with it from there. So thank you for watching the video. Thank you and have a nice day.